out of the way and go full screen. All right, yeah, so Sanjay and I are here covering the one pixel attack for fooling deep neural networks. We can jump right in. It was published in January 2019. Authors from the Kyushu University in Japan with this Koichi Sakurai, works for a research institute. The major motivation here is that as we see, deep neural networks are commonly used as image classifiers. They're very good at it. And like covered in the last presentation, perturbations can be used to create an adversarial image that can fool those classifiers. One of the things that the authors really wanted to look at here is that when you add perturbations, they're not necessarily imperceptible. You might be able to see them with the naked eye, or you might be able to have your network understand that there was some change, something that's off about this image. So they wanted to limit the number of pixels that are modified. So the first step here is in generating an adversarial image. They wanted to view it as an optimization problem. So I wanted to go through just the basic. I like to do this anytime there's a big formula here. So they say F is their image classifier, X is the natural image that they're going to perturb, T is that the class, the actual class of the image. There, F of X is the probability that X belongs to that class T. E is their the additive perturbation vector, so what they're going to use to add to the image to change it. ADV, so the short for adversarial, I assume, is the target class, and L is a limit of the maximum modification, so essentially the length of the vector. And we see here that the general form, they want to maximize E, their additive perturbation vector with the constraint that it's smaller than the limit of their max modification. The authors take that a bit further and they say, instead of L, they're going to use D. I think I have on the next slide. Their approach specifically is D is a small number, really 1 in this case. So they want to modify 1 pixel and have that fool the classifiers. So yeah, in general, you're trying to find which dimension you're going to perturb and how strong of a modification for each dimension. But those authors are saying, we're going to hone in on 1 single pixel. We're going to modify that and try to fool the classifier. So to do that, they decided to use differential evolution, which is it's a population-based optimization algorithm. It's part of the general class of evolutionary algorithms. So there's a whole class of different evolutionary algorithms that differential evolution is part of. The population selection that it has allows you to efficiently find better solutions than gradient-based solutions or other evolutionary algorithms. And basically, the way it works is it iteratively tries to improve the candidate solutions. So you start out with your candidate solution, with a group of candidate solutions, and each iteration, you generate another set of candidate solutions based on your current population. Those new solutions are compared with their parents, and basically whoever fits, produces a better fitness value, survives to the next generation. So as you're going through multiple generations, you're constantly improving the fitness value of your solution while having a diverse set of solutions, or solutions. So this is kind of on the right here, the idea that you have an initial population, you are going to mutate that each generation, recombine them, and take a look at what you have, select your best options, and then say, is this our termination case? Did we reach the fitness level that we want, or do we hit some other termination case that we predetermined? If not, we're going to go back and mutate again, recombine, select over and over multiple generations until we have our optimal solution. The major advantages here are that it's less subject to local minima than gradient descent or greedy search algorithms, which gives you a higher probability of finding your global optima. It doesn't require the optimization problem to be differentiable. You don't need to know as much information about the target system. Like we covered in the last paper, they had a white box attack where they had to understand so much about the system that they're attacking. Here, this acts more as a black box attack. The only thing you need to know is the probability labels for the system. Your problem doesn't need to be differentiable, so it's much easier to come up with an answer. So the methodology here that they used in their experiments, they started with an initial population of 400 candidate solutions. They encode those into an array that's going to be evolved by differential evolution using this formula, where so X is the element of the candidate solution. R1 through R3 are going to be random numbers, and F is a scale parameter that their scalar they just set to 0.5. G is your current index of the generation. So essentially, your next generation is going to be an element of multiple different candidate solutions that you had before. Well, we'll say your first one. So XR1 is one candidate solution from the previous generation. Then the difference between two other XR2 and XR3 candidate solutions multiplied by a scalar and added. So that's the mutation and recombining to create your next generation of candidate solutions. So as they go through each one of those generations, each iteration, the candidate solutions compete with their parents and the winner moves on to the next round. They set their maximum number of iterations to 100, and their early stop criteria was they split between for targeted attacks. They would look at the probability label of the target class exceeding 90%. So if they were explicitly trying to say this dog image is a cat image, they want their candidate solution to have a 90% chance to say that's a cat specifically, not it's something else, a deer or a bird or anything. Whereas a non-targeted attack, they did the opposite. They actually looked for the label of the true class to be lower than 5%. So they said, instead of looking for explicitly getting to our new class, that the chance that we maintain the actual class is drastically smaller. So their true class label was compared to their highest non-true class label to evaluate if the attack succeeded. So essentially, was there some class that the classifier thought it was more likely the image would be than the actual class. So it could still say, well, there's a 40% chance this is a dog, but if you hit 41% this is a cat, they say, yeah, that's a cat. Okay, that's success. They set up their initial populations with uniform distributions. They used the CFAR 10 images for one set of experiments. The uniform distributions were 1 to 32. That's based on the size of the images. And for ImageNet, they use a uniform distribution of 227, again, based on the size of the images they had. And then that fitness function that they used to try to optimize is, in the case of CFAR 10 data, it's the probabilistic label of the target class for that image. So that's basically kind of a reiteration of the early stop criteria. And then for ImageNet images, they did the non-targeted attack. So the label of the true class, they wanted to make sure that their attack said it was something other than what it was. They didn't care what it was. And then I think we're swapping over to Sanjay here. I think he's gonna share his screen instead.
Yes, okay. So some of the evaluation metrics that the authors used in this paper is the success rate. So for the targeted attacks, the success rate would be the probability that the image was misclassified as a specific class. That would be the success rate. And then for the non-targeted attack, the probability of the image being misclassified to any other class will be the success rate. And then one other metric of importance is the confidence or the adversarial probability labels here. And that's the average confidence of the misclassification image. So if the system misclassified an image as a cat, over different over multiple iterations of that image, what's the average probability that it was misclassified as a cat? And then we have the number of target classes, and then we also have the number of original target class paired. But the most important are the success rate and the confidence. And then the authors use the Kaggle's CFR10. This is a slight modification to the original CFR10, where they have some modifications such as duplication, rotation, clipping, and blurring. And then the authors use the three neural networks, which is the all convolution network, and the VGG16 as an image classifier. They trained this model on the CFR10 dataset, and then they launched both the targeted and the non-targeted attacks. So this CFR10 is a collection of 32 by 32 images. So it's a pretty small image. And then they ran additional experiments as well, not just the single 1 pixel attack. They used 3 pixel and also 5 pixel attacks. And then for the targeted attack, for each image, they try to misclassify that particular image as 9 other classes. So it's a pretty exhaustive targeted attack. And then one small point to note here is that the targeted attack is a small subset of the non-targeted attack. So if the targeted attack works, you could assume that the non-targeted attack is successful as well. And then the other data set that they used here is the ImageNet. The ImageNet is slightly bigger. It's approximately 50 times bigger than the CFR10. And because this ImageNet is bigger, they did not try using targeted attack. They used non-targeted attack, where the fitness function, it aims to decrease the probability of the true class. Instead of trying to misclassify it into a specific class, it just tries to decrease the probability of the true class. And then they conducted only the 1 pixel attack on this data set. So the results of the 1 pixel attack, if you look to the right here, you see the original accuracy of all 4 networks. So the first 3 are for the Kaggle CFR10, and then the last column is for the ImageNet dataset. And they used BVLC LXNet, which is a slight modification of the regular LXNet network. So this last column is for the ImageNet. So looking at the first column or the first row, these are the original accuracies of the network. And then the second row is the success rate of the targeted attack. So if you look at this if you look at the numbers of the all convolution network and VGG16, you can say that approximately 15 to 25% of the images were successfully misclassified as one other class. And then the non-targeted attack, it's much higher than the targeted attack because there's no constraint to misclassify it as a specific image. So looking at these numbers here, a few key insights here is that if you look at the network in network, the attack success rate for both the targeted and the non-targeted attacks were slightly higher compared to the all convolution and the VGG16. So this would indicate that the network in network model that the authors used here is less robust and more prone to the attack. And then we also have the results for the 3 pixel and the 5 pixel attack. The success rate of both are shown here, and they are slightly higher than the success rate of the single pixel attack. So that would indicate that by increasing the number of pixels from 1 to 3 to 5, you increase the success rate of both targeted and the non-targeted attack. And the confidence score across all the networks is pretty high. So the network was confident when it tried to misclassify an image. So that would indicate that the attack worked properly. And then some comments about the AlexNet network trained on the ImageNet dataset. We have a lower success rate here because the dataset is so much larger than the CFAR10. So 1 pixel will be a real small portion of the whole entire image. So the 16% number here that you see in the non-targeted attack, it's quite significant when you consider the fact that we just modified 1 pixel out of 227 by 227 pixels. And then the confidence score of the AlexNet is it's lower because the AlexNet or the ImageNet, sorry, the ImageNet has 1,000 classes compared to 10 for CFAR10. And then a few other key points here to note is, so the authors found out that a few target pair classes were more vulnerable. So for example, if you see the cat, the image of a cat here, by changing this 1 pixel, the network misclassified it as a dog. So this cat pair dog is more vulnerable to this change. So it's easier to misclassify a cat as a dog and vice versa. Another important point here is that if you look at the heat map, the numbers in red are the classes before the attack, and the classes after the attack are in blue. So if you look at this, the class 3, which is a cat, the authors had higher success in misclassifying it as a dog, which is labeled with the number 5. And this same is true when the authors tried to misclassify the dog as a cat, they had higher probability. So it's the heat map is symmetric, which means there are a few target pair classes that are more vulnerable and that are interchangeable. There are a few outliers. For example, this 8, the number 8 is a ship, and you can misclassify it as an airplane with a high probability, but the inverse is not true. So if you try to misclassify an airplane as a ship, that did not work here. So there are a few outliers here. And then they tried to evaluate if the differential evolution algorithm was a good algorithm. So to do that, they compared the differential evolution with the random 1-pixel attack. So the random 1-pixel attack, the way it works is they randomly change 1 pixel in the image to any other value and test out if that fooled the network. So comparing the first two metrics here that you see, the success rate and the confidence, is for the differential evolution algorithm, and the next two is for the random 1-pixel attack. So comparing the differential evolution and the random success rate, the differential evolution had higher success rate compared to the random. So that would imply that the differential evolution found a better optimal solution compared to the random search. And then one key point here is that the random search for VGG16, it did not work as good as the differential evolution. So that would indicate that VGG16 is slightly more robust to a random attack. And then, yes, so this is, if you're wondering what the fitness value would be over different generations, this is the decrease in fitness value. So our goal is to decrease the fitness value across generation. Fitness value would be similar to a loss when you train the system. And visually, it looks like a loss function across multiple iterations of the training. Initially, you see a large drop in the fitness function, similar to a loss. So you can safely assume that it does not take 100 generations to reach an approximate good solution. It takes maybe 10 or 20 generations. And then since the original data set was for the Kaggle data set, they compared it with the original CIFAR 10 data set. Since CIFAR 10 data set has much less noise, the networks were trained properly, which is why you see that the first two columns is for the original CIFAR 10, whereas the other are for the Kaggle CIFAR 10. So the numbers for the original CIFAR 10 are much lower, indicating that the attack was not as successful. And then as successful as the Kaggle CIFAR 10. And then the same trends holds true, that the network is less robust compared to all convolution and VGG16. So there is some carryover of results across two data sets. And then the authors still found some vulnerable original target class pairs. One curious point to note here is this, believe it or not, is an image of a dog, which I had trouble figuring it out. But this is a dog, and this dog was successfully misclassified as all of the other classes shown here by modifying these pixels highlighted here. So, and the confidence, the interesting point here is that the confidence of the misclassification was close to 100%, which is surprising. But this is just my hypothesis. The reason why this is possible, this could be possible, is because this image of a dog does not have like really strong distinguishing features. So the eyes, the nose, the paws, the tail, you can barely make them out here. So that could be one reason why this was the case here. The attack worked so well here. And then this could, another reason could be that this image of a dog is completely dissimilar to all the other images of a dog. So final conclusions, the 1-pixel attack was successful in fooling a lot of networks on a variety of data sets. And then there are a few detection mechanisms to detect these changes in the data set. But so far they were too expensive, either computationally or resource intensive. So so far there were no detection mechanisms for this, no good detection mechanisms for this attack. And then the next part is the use of differential evolution. So usually we use like a gradient based optimization algorithm, but this paper shows that the differential evolution algorithm worked well as well. And then differential evolution algorithm is more flexible, considering that you don't need the function to be differentiable, which is the case for this attack. The function that they used here is not differentiable. So they were kind of limited to this differential evolution algorithm, and the gradient descent based optimization would not have worked here. So that's it for my presentation. Any questions?